today we're going to finish up our BFFs and do a little review, and then maybe do a little new stuff too. So first of all, let's get out our BFF cards. We've already done the first 3. So again, you're going to label your cards with name, equation, and graph. Okay? So the next function we're going to talk about is the reciprocal function. And its equation is y equals 1 over x. Its shape, an asymptote on the y-axis, an asymptote on the x-axis, and a hyperbola, curve that looks like this, in quadrants 1 and 3. That is your reciprocal function. Next, we have the square root function. And its equation is, as you probably guessed, y equals the square root of x. Now be careful with its picture. You're going to put a dot right here at the origin, and then you're going to kind of go arc out and up like that. That is your square root function. Think of it maybe as the top half of a sideways parabola, if that helps you draw it. It's the top half only of a sideways parabola. That is your square root function. Then we have the exponential function, exponential, and its equation is y equals e to the x. Now, that e, you might think stands for exponential, but it doesn't. That e is Euler's constant. We'll talk more about that later. This does not need to be on your note card, and it's nothing you need to know right at this moment, but that's what that e is. But it is the exponential equation, so you can kind of tie the two together if you wish. That equation has that curve has an asymptote on the x-axis, a dot at 0, 1, and then it looks like this. So as it goes to the left, it gets closer to its asymptote, and as it goes to the right, it starts shooting up into space. Okay. What do we got next? Now we've got the logarithmic function. The logarithmic function, logarithms, and the equation we use is y equals ln x. That's called the natural logarithm. We could also use log x. It doesn't make any difference. Those are the same basic shape. The same basic shape. This one has an asymptote on the y-axis. I kind of missed there. That's an asymptote on the y-axis. And a point at 1, 0. Please do not get this one mixed up with the square root function. Look back a couple cards ago, the square root function. It kind of has that shape, but the difference is the square root function just starts at the origin and shoots out and up. This one does the out and up thing, but it also goes down, 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 down. Okay? So this is your square root function. And this is your logarithmic function. Now we have the sine, and the cosine. These are our trig functions. The equation for sine, this is called the sine function, is sin x, sine x, but it's abbreviated sin. Looks like sin, but it's called sine in math class. Now, on your note card, this one's a little bit trickier. On your note card, I want you to label up here 1 and down here -1. Then I want you to put a dot. We're doing the sine. So I put a dot right here at the origin. We're going to make a hill that goes up 1. And then you're going to make a valley that goes down 1. And then you're going to arrow on that, because guess what it does? It makes another hill and another valley and another hill and another valley. And it goes that way too. So we've got a valley and a hill this way too. And it's kind of bouncing back, that's not very good, kind of bouncing back and forth between 1 and -1. That is your sine function. Now your next card is going to be cosine. That equation is cos x. Cos, cosine, cos. And you're going to draw a picture that is almost the same. So you're going to put a 1 up here and a -1 down here. And we're going to draw hills and valleys. The difference is, instead of starting at the origin, you're going to put a dot up here. So with the sine, we have a dot at the origin. This is kind of goofy, but original sin, original origin, sin, original sin. The sine goes through the origin. The cosine, this is actually going to be the top of the hill. So here's our hill and here's our valley, and there it goes. And here's the rest of the hill and the rest of the valley, and there it goes. So the two pictures, sine and cosine, are basically the same, except the sine starts at the origin and makes a hill. The cosine starts at the top of the hill. And both of them are bouncing back and forth between 1 and -1. Just up and down, up and down. Okay, you're almost done. 3 more. We have the absolute value function. And its equation is y equals absolute value x. This one I think you studied quite a bit in Algebra 2, so you probably remember that its sketch is a V. So you'll want to keep this one straight from the squaring or the quadratic function. The squaring function, remember, is a parabola. So you need to make sure they're very, very similar. This is a V, absolute value. This is a U, a parabola. So you want to make sure that your absolute value has a nice sharp point, but your parabola is nice and rounded. Now we have the greatest integer function. And there are a couple of different notations for this. If you look in a book, a lot of times you'll see like a bracket. Sometimes it even has little lines inside of the bracket. If you look on your calculator, it says INTX. As far as I'm concerned, you need to know one of those notations, one of those equations, but I may use both of them from time to time, so you'll want to be familiar with both of them. Greatest integer. This one's kind of tough to grasp, so try to follow along here. We're going to put a nice solid dot. I'll make mine kind of big. A nice solid dot at the origin. Then you're going to march over a little ways. It's actually 1 unit, but just go over a little ways and put an open circle. Then go up and put another closed circle right above that open circle, and then march over the same distance you did down here, straight across, and make an open one. And then closed. And then the steps not only go up here, but they also go this way too, so we can continue it this way. So what makes this tricky is sometimes we get confused about where the open dots are and where the closed dots are. That's why I recommend that you always start by putting a closed dot at the origin. Then you'll know it's closed to open, and then closed to open. Okay? And then the last one, we have what's called the logistic function. And the logistic function is got a crazy equation. Absolutely crazy. 1 over 1 plus e to the negative x. That is the hardest equation, no question about it, but that's the equation of the logistic function. Luckily, the picture's not so hard. The picture has an asymptote right here on the x-axis. And then go ahead and come up and label that 1. There's an asymptote up here at 1. And then remember the squiggle that was the cubing function? We kind of have the same kind of squiggle happening here, but it's sideways. So it follows this line out, and it follows this line out, and it kind of squiggles a little bit in between. Those are your BFFs. Okay, all right, let's put those note cards aside. Remember, you do need to spend some time studying, because at some point we're going to have a quiz, and the quiz is going to mean or require you to know the name of the function, the equation of the function, and the graph of the function. We'll practice. I've got several practice quizzes, but your job right now is to start memorizing these things with your flashcards. All right, so set those aside, put them together with a paper clip or a rubber band or something. We don't want to lose them. Sometimes kids put them in a baggie. That's a good idea too. Just some way of keeping them all organized, because you need all 12. All right, let's get on our notes packet now. And we are going to look at page 9A of our notes. It's actually numbered 9A. And it's called Practice Domain Range Holes and Asymptotes. Okay, so here we go. Problem A says find the domain. Now, you guys, we have done enough of these. You know that when the question involves domain, you know that you have to zero in on 2 things. You have to zero in on the denominator that can't be 0, and you have to zero in on whatever's under the radical has to be greater than or equal to 0. Okay, so in our very first problem here, A, we have both. We have a denominator, so x minus 2 cannot be 0, which means x cannot be 2. So there is part of our domain. This tells me that I can pick whatever x's I want except 2. Okay, now what is under the radical? Well, under the radical, I have x plus 1. Guys, remember, don't include the radical. It's what's under the radical. X plus 1 is greater than or equal to 0. So x is greater than or equal to -1. And there is your domain. Any number bigger than or equal to -1 except 2. Those are the numbers that x can be. That's your domain. All right, let's look at this guy. Domain. So these are my considerations. Does this problem have a denominator? No. Does it have a radical? Nope. No denominator, no radical means no issues. So what's my domain? If I have no issues, if I have no limitations, no restrictions, then my domain is -infinity to infinity, or you could say all real numbers if you prefer. All right, last one, domain. There's no denominator to worry about, but there is a radical. So what is under the radical is 2x minus 5, and according to our rules, what's under the radical has to be greater than or equal to 0. So 2x is greater than or equal to 5, and x is greater than or equal to 5/2. Now, I put 5/2. If you put 2.5 or 2.5, that's fine. That is your domain. All the x's bigger than or equal to 5/2. All right, that takes care of part 1. Okay, now part 2, we want to talk about where are the asymptotes? Vertical, horizontal, and holes. All right, so let's talk about that for a second. The only way to get a hole in your graph is to cancel something. Is there anything in this problem that's going to cancel? No. No. If you can't factor it, you can't cancel it. So nothing there cancels. Don't even think about it. Nothing cancels. You know, we had problems where we had this kind of stuff going on, right? That's when we can cancel. If these two match, we cancel them out. You don't cancel in a problem like that. All right, what about a vertical asymptote? Well, remember, your vertical asymptotes come from the denominator. So where's your vertical asymptote? You know this. Your vertical asymptote is at x equals -5. Because if you put -5 into your problem, you get 0 down here, and that's not allowed. The denominator cannot be 0. So you have an asymptote there. All right, and what about your horizontal asymptote? Well, this is newer. We haven't done many of these. But remember, to find your horizontal asymptote, you box in your x's. So looking at my problem, I'm going to box in my x's. So I have two x's over one x. I have 2 over 1. So my horizontal asymptote is at y equals 2. 2 over 1. 2 over 1. Y equals 2. Problem B is harder, bigger, but we can do it because we know what we're supposed to do. What are we going to do first here? You know, I hope you're already doing it. I hope you're getting ahead of me. And I hope you're factoring that thing. I always like to do the bottom here. That's easy, right? That's the difference of squares. So x plus 1, x minus 1 on the bottom. Now the top, this is where we sometimes get confused. We don't need to get confused. We need to jump in and then check our answer. So I know that whatever I put here has to multiply to be -5. So I'm thinking 5 and -1. It has to multiply to give me -5. Okay? Now when I FOIL it, I'm focusing on, do I get -4 in the middle? Well, let's FOIL it and see. I get x squared, I'm FOILing the top, x squared minus x plus 5x minus 5. This looks good, this looks good. But what about the middle? That gives me a +4, I need a -4. So I'll just make this a minus, this a plus, and now I'm good to go. Guys, you just need to factor, and then you need to check to make sure you factored right. And if you didn't get it right, you need to try again, just like I did. Now, what do you notice? Woo, we got cancellation. That means that this problem will have a hole. And the hole will always be a point. So it's an x comma y. And the x, oh man, I hope you remember, the x comes from whatever we canceled out. So we canceled out an x plus 1. So my hole will be at -1. The opposite of this. Then, because it's a point and I need a y, I need this part, I'm going to take that -1 and I'm going to plug it right back in right here. Not the original problem, it won't work. You need to put it in here. So if I put in -1, I have -1 minus 5 and -1 minus 1. -1 minus 5 is -6. -1 minus 1 is -2. And that makes 3 when I reduce it. So in terms of my picture, at -1, 3, I have an open dot. Now let's look at this right here. This is where we're looking. Do I have any vertical asymptotes? Vertical asymptotes come from the denominator. Always make a note of that if you forget. It comes from the denominator. It cannot be. It's the domain. Obviously, in this problem, x cannot be 1. So that is going to be my asymptote. My vertical asymptote is at 1. Because if I put 1 in there, I get 0 in the denominator, and that's not good. All right, now my horizontal asymptote. Remember how we do horizontals. Verticals come from the denominator. Horizontals come from making the box around the x's. Now what have I got? I got a 1x over a 1x. I have 1 over 1. Well, 1 over 1 is 1. So my horizontal asymptote is y equals 1. X over 1x. That makes 1. Here we go. Problem C. What are we going to do first? What do we always do first? What do we do first over here? We always factor if we can. Well, the top does not factor. But how about the bottom? The bottom is the difference of squares. Now, I could factor, but could I cancel? No. So therefore, there are no holes. Because the only way you're going to get a hole is if you can cancel out one of your factors. We can't, so we're going to no holes. How about vertical asymptotes? Well, look, now I'm going to have 2 of them. Remember, vertical asymptotes come from the bottom. So I'm going to have a vertical asymptote at x equals -2 and x equals +2. Opposite would be -2, opposite would be +2. Now what about horizontal asymptotes? Well, remember, how do we get horizontal asymptotes? We box them in. Now remember though, this is the tricky part. You have to box in the highest power. And it has to be that power on the top and the bottom. So in other words, I can't box in an x and an x squared. I can't do that. This is my biggest power. So when I box in, it has to be x squared over x squared. Well, I don't have an x squared up there, so I'm going to add 1. I have 0, x squared on the top. And now I can box it in. So I have 0 x squared over 1 x squared, which is 0 over 1 or 0. 0 divided by 1 is 0. Always and forever. So y equals 0 is my horizontal asymptote. And now I have finished with that problem. Remember, we're working our way toward graphing the whole thing. Right now we're just putting in what are called the discontinuities, the asymptotes and holes, the things that break up the graph. And I'm sure you're just tickled pink that we got another one. We have one more. On this review and practice sheet. So y equals x squared minus 4 over x plus 1. What is the very first thing you need to do? The very first thing you need to do is factor if you can. Does anything factor? The numerator, the difference of squares, x plus 2, x minus 2, and of course the denominator doesn't. Does anything cancel? No. So there aren't any holes. Somebody asked the other day, can two things cancel? Can your picture have two holes? And the answer is yep. You can have, every time something cancels, you're going to have a hole. So if you, every time an x cancels, you're going to have a hole. So if you had two factors cancel out, then you would have two holes. If you had three cancel out, you'd have three holes. In this case, we have nothing canceling out, so we have no holes. All right. What about a vertical asymptote? We have one. Our vertical asymptote comes from the denominator. It's x equals negative 1. Vertical, x equals negative 1. Well, what about horizontal? Let's look back at the original. Remember, to do horizontal, we box something in. We always box in the highest power. Well, what is my highest power? X squared. Oh, I don't have any on the bottom, so I have to put one down there because that is the only way I can box in. So now I have 1x squared over no x squareds. Wait a minute, 1 over none. 1x squared over no x squared. Is that doable? Absolutely not. So there is no horizontal asymptote either. Picture might seem a little boring. That would actually be a really cool picture when we get around to actually sketching it. But in terms of discontinuities, that's all it's got right there. All right, so that was good review and practice. Now we're going to go to page 10 of our notes. And I need you to get your BFF cards out, get your flashcards out, because now we're going to be sketching some of these weird shapes, some of these BFFs. But we're going to be moved around a little bit. So we need to talk about the different the ways equations or pictures can be moved. So I am on page 10 of my notes. You have out your BFFs, which we just completed, so you should have all 12 of them kind of handy there. Get them out and have them ready. And we're going to sketch, this is problem A, we're going to sketch x minus the square root of x minus 5. Now, notice it's a square root. So this picture is going to look like the square root function. So find your square root function on your note card and look at the picture. I know you don't have it memorized yet, that's fine. Get it out on the note card and look at it. You should see a shape that has a dot at the origin and shoots up and out like this. That is your square root function. This picture is going to look just like that. The difference is when you add and subtract, you move it. Take really good notes if you don't already know this. I know you did this in Algebra 2, but maybe you forgot. Take really good notes. If you are adding or subtracting inside the problem, so what I mean is, as opposed to this, where the 5 is outside of the radical. if you're adding or subtracting inside the radical, it's going to be shifted left or right. It's a sideways shift. X minus 5 goes to the right. X plus 5 goes to the left. Now, that might seem counterintuitive, but not if you think about it. Because all along, we've been talking about when we had something like this in the denominator, it went left 1, the asymptote was at -1. Same principle here, okay? So we're going to take that picture and we're going to move it 1, 2, 3, 4, 5 to the right. And you're done. That's all there is to it. So the beauty of knowing the shapes is that now you can sketch any square root just like that. You have to know what the shape is, which you're going to memorize your BFF, and then you have to remember the rules. When we have a plus or a minus inside the problem, it's left or right. Minus is right, plus is left. Obviously, I can't remember this. Yeah, you can. You need to remember it. But we're going to practice. We've got a whole bunch over here, and we've got more on another practice sheet. All right. So what's the next one? B, letter B. Now we're going to sketch absolute value plus 1. Now get out your BFF card for the absolute value. And what shape is it? I'm going to draw the shape over here. What shape is it? It is a V from the origin. That should be on your note card for the absolute value. Now notice I'm adding, but that add is not inside the absolute value sign. It's not this. This one was inside the square root. This one is inside the absolute value. When you're adding or subtracting inside, you're going sideways. Well, this one I'm not adding inside. This one I'm adding outside. Adding outside moves you up and down. Plus 1 means up 1. So my V is going to go up to this point, up 1, and then V from there. So if the number is added outside the problem, it's up and down. Plus is up, minus is down. Yep, you gotta remember the rules. We go over one more time. If the number is added or subtracted inside the problem, so under the radical, in the parentheses, in the absolute value, if the number is inside the problem, added or subtracted, it's left or right. Minus is right, plus is left. If the number is outside the problem, added or subtracted outside the problem, plus is up, minus is down. All right, let's look at C. All right, so two things I want you to think about first before you even get started. Which BFF is this? Look at your cards. It's your exponential. And it looks like, under normal circumstances, just a regular exponential has an asymptote here on the y or the x-axis, a dotted 0, 1, and up like that. That is your regular exponential. So that's the shape. Now we're moving it. How are we moving it? Well, is that hooked directly to the X? This one's kind of different. If it were, it would look like this. See how that +1 is hooked directly to the X? It's inside the problem. Here is my function. And then outside of that, I'm adding 1. So I'm adding 1 to the end of my problem. That is up and down. That's a shift, up and down, called a vertical shift. We're going up and down. Since it's a +1, we're going up 1. So take that picture and move everything up 1. So instead of the asymptote being here at 0, now the asymptote is going to be up here at 1. And instead of the intercept, the dot, being at 1, it's now going to be at 2. And then I have my same shape. Remember, you aren't changing your shape. Whatever the shape is on your note card, that's the shape you're going to have. It's just going to be positioned a little differently. Okay, D. Which BFF shape are we starting with in this problem? Which of your note cards does this problem correspond to? I hope you're thinking the squaring function. I hope you're thinking the quadratic, the parabola, the U, squared. So now you have to decide, am I going to take my parabola left, right, up, or down? If I'm going up or down, the problem would look different. If I were going up, it would be x squared plus 1. See how the 1 is outside the x, away from the x? If it were down, it would be x squared minus 1. So this one is left or right. That plus 1 is inside the parentheses, so we're going left or right. You have done this a million times with your asymptotes, with your domain, with everything. You've done it a million times. X plus 1 is going which way? Negative 1. So this is going to the left, 1 unit. Right would be x minus 1. That would take you to positive 1. Remember, you're moving this point. That tells you you're now going to be at negative 1. So here is your parabola. Remember, it's a parabola, not a V. So make sure it's got some curviness to it. Those straight lines, that would be absolute value. I'm going to leave this here for you to look at, maybe write down, because that kind of summarizes the ways we move things when we add or subtract. They're called translations. We can have horizontal or vertical translations. Okay, we have one more. Okay, guess what? The one that's left is another parabola. Would you agree with that? I erased mine. you agree with me that problem E is another parabola? It's x squared. And I kind of gave it away here, but do you notice that the -1 is away from the squared? It's not part of the squared. Here it was part of the squared. It's away from the squared. So that means I'm going up or down. Negative means I'm going down. So I'm going to take my parabola, that exact shape, my squaring shape, and I'm going to move it down 1. Get in the habit of labeling those important points, the vertex. So instead of being at the origin, it's been dropped down 1. Okay, well, I think that's enough for this video. So we'll pick up, do a little more practice with this, and some piecewise functions next time. And then we'll be just about done with this section too. Make sure that your 1.2 homework is done by Tuesday. We've practiced.